Today we are continuing through Chapter 2. On the last lecture, on lecture number 10, we had sort of an overview of Chapter 2, which is about strain or changes in the dimension of an object based sometimes on a load. In this case, we're talking about something that's being loaded. There are other things that change the dimension of an object, such as temperature. Most objects will expand or contract due to higher or lower temperatures. One example of that you may have seen is sidewalks, concrete. If it gets too hot, they'll kind of heave up if the expansion joints aren't big enough. So that's one example. In a good design, everything has big enough expansion joints that the changes in length will not cause heave or rupture. So anyway, but what we're talking about today specifically is a strain or change in length due to a normal stress. So coming over to the document camera, we're going to kind of illuminate this again. And in mechanics of materials, we often do this where we look at two different things. We look at normal stress, so it's kind of based on geometry, and normal strain. That's not really a versus. Normal stress that leads to normal strain. And then later we'll look at a shearing stress that leads to a shearing strain. Another very fundamental definition or division for our discussion is the idea of elastic behavior versus plastic behavior. And elastic is like an elastic band or a rubber band where we rebound back to an original condition when the stress is removed. Plastic is where the rebound is incomplete, or it can even be a failure of some sort, whether it's a rupture or a change in the physical properties of the material. So on our graph, which is once again fundamental to our discussion, when we plot sigma versus epsilon for a normally behaving homogeneous material, when we have 0 sigma, we also have 0 epsilon, and we continue in a straight line fashion until something happens. So the something may be a ductile yield, it may be a brittle rupture, or it may be something in between. But the answer, or the point that I'm working with, is that this is the elastic region, and this is the region that we are talking about today. And actually for the entirety of this class. You'll deal with plastic behavior and rupture in other classes. But for us, elastic is the region that we're talking about. So in the elastic region, we can also see that this is basically a straight line, and the slope of that line is called E, which is the modulus of elasticity, and it's also called Young's modulus. But since this goes through 0, E is equal to the slope of this line, which is sigma minus 0 over epsilon minus 0. Or because these are zeros, it's just sigma over epsilon at any given point. Now, the units or the dimensions of epsilon, of course, of sigma are a force per area or a force per length squared. And the dimensions of epsilon are nothing, dimensionless, because it's a length over length. So that means that the dimensions of the modulus of elasticity are this over this, which is just force per length squared. Okay? Now, the other point is the value of E indicates this non-technical term, the stretchiness of the material, not the strength So in other words, it's really important to remember that the modulus of elasticity tells you nothing about where rupture or yield is going to occur. You can have a material like this, or you could have a material like this with profoundly different strengths or ultimate or yield or rupture sigmas, but the E is the same if the straight line portion is the same. And that E and the strength of the material are actually physical characteristics of a material. So if you don't know what a material is and you're testing it in a laboratory, when you determine the value of the modulus of elasticity and where it fails and how it fails, that will give you an idea of whether you're dealing with, say, aluminum or titanium or tungsten or cold rolled steel or whatever the material is. So that's kind of a fundamental property of a material. Maybe not fundamental, but it's an important property of the material. So why do we not want things to fail? Why do we only design in the elastic region unless we are very, very knowledgeable about a particular material and a particular application? Well, there's an old expression that says failure is not an option, but I guarantee that failure is an option. But failure is of a material. I'm a fan of failing in like real life, like trying something and it doesn't work. I think that's a great way to learn. But when you're talking about structures and materials and machine parts, failure is expensive. It is time consuming. And it is also dangerous. It can threaten human life. It can threaten lives in general. It can threaten other machine parts. If something fails, it can cause other things to fail. Now, in another instance, sometimes a part is meant to fail. And I have one here that did not fail as it was supposed to. So I'm going to pass this around in just a minute, but I'll describe it and then I'll put it up. This is a part of it was a shaft in a piece of farm equipment. But one example that you may be familiar with in terms of something that is designed to fail, to prevent other things from failing, are fuses, like in your car or in your house. If you overload a circuit, the fuse is designed to be less. Yes, Christian. What's that? Yes. Coupling. Yes, absolutely. That's right. And that's a great example as well. Something is designed to fail that you can get to easily that is inexpensive. That's a good design. So like with, and I'd like to hear a little bit more about that in just a second because that's a great example. So if you have a fuse and the fuse costs 50 cents and you have a circuit behind it or that goes through that fuse that costs $500, you want the fuse to fail. And then if you're smart, it also indicates to you that it's time to not only replace the fuse, but if it fails again, that you have too much juice going through your circuit, juice being the, not a technical term, too much current going through your circuit or too much resistance in your circuit or something, so that you need to redesign that circuit so that it doesn't happen again. Talk to me about coupling for a minute.
What should I say?
Oh, what do you think? Just tell me your opinion of a failure with a coupling that is an appropriate failure.
Yeah, I know the pressure on coupling should
Yes.
be lower than the output protect.
Perfect. Yes, and I didn't mean to put you on the spot, but that's a beautiful explanation. That's exactly right. So the coupling will fail first so that the rest of the equipment behind it will stay safe. So it's the first thing to fail. Very good. This is something that was designed to fail in a certain way and did not do so. And I'm going to pass this around. I don't know if you can see this, but I'm trying to put this so it can be on my video. But basically what happens here, there's a little square object. Let me get a pointy pen right here. Right here, which is called a drift key. And this is spinning. These splines are spinning and spinning and spinning. And what's meant to happen is if there's too much power that goes through this shaft, this key is supposed to fail. And then what it'll do, it'll just go into free spin, but it won't blow up the entire thing. Well, as you can see on this, that did not happen. And it blew up, right? So the key is intact, right? This is a problem. Everything else is destroyed. You can see that this place where the bolt goes into it, there's a rupture here. All of this entire shaft twisted off, and yet you can see the key down below, and the key up above is just fine. So this is not a good failure. This is not the way you want it to fail. You wanted that key to fail. So I don't know what happened if the key was replaced. Maybe the key was breaking all the time, and somebody said, you know, that is just so annoying. I'm gonna machine something that's stronger, and I'm gonna keep that key from breaking. I do not know the specifics of it, but it's quite a dramatic, So have a look and then pass it around to your classmates. So you can take a look. Yeah, it was, that was pretty dramatic. So I have some other failures I may show you in a little bit here. But there's another interesting thing, and it turns out that by the way a structural element fails, you can have an idea as to whether it's more brittle or more ductile. So there's another distinction, brittle or ductile. And what it means is brittle things tend to fail catastrophically, and they also tend to fail in normal stress. So that means you pull on them and they come apart, and the surface of breakage will be pretty square, like this. Now, if, on the other hand, something that is ductile fails, it will tend to fail more on a 45-degree angle. And that's because it tends to fail on shearing stress. And in the real world, of course, you have both normal stress and shearing stress. But in general, this is sort of indicative. And I don't know if you recall, but when we talked about those oblique surface failures, or the stress, normal stress, and shearing stress on an oblique surface, we indicated that tau was P over A0 times the sine of theta times the cosine of theta, whereas sigma is P over A0 times the cosine squared of theta. Well, what that indicates, because the cosine of 90 degrees is 1, indicates that you're going to have a maximum sigma at 90 degrees. When you do the math on this and you take the first derivative of this expression and set it equal to 0 to find a max or min, you'll find that the max occurs at 45 degrees. So this indicates a failure in sigma. This indicates a failure in tau. This indicates a failure in sigma. And if you're in between, it's failing in some combination. But A naught, absolutely. And that's a very good point of clarification, because remember we have A naught, and then we also have A theta. So if we drew this surface again, this surface would be A theta, and this surface would be A naught. Oops. There we go. You know, when I post these videos, it's very strange to me because about 3/4 of the time, both of my hands are on the page like this. Maybe you guys are used to looking at that. And I'm so predominantly left-handed, and that's like the only thing I see on the first part of the videos. So, but you know, I've gotten by this long without writing with my right hand. So I guess it's not going to change at this point. Anyway, there we go. So there are some ideas. Now let's get back to the topic of the day, which is elastic region. Epsilon caused by sigma. That's what we're going to talk about today. We're going to get some equations today so that we can work some stuff. Now the first part is, if you exceed, they refer to this point, whether it's sigma yield or sigma rupture or whatever, the elastic limit of the material, these equations are not valid. So we are only talking about what's going on here in the elastic region. That's it. All right, so let's go ahead and develop some equations. We know that on this graph, we go through 0. We have sigma on the y-axis, epsilon on the x-axis, and the slope is E. So this is actually in your textbook. This little, it's not really a derivation. It's just a sort of an explanation, I guess I would say. So this begins on page 68. Let's see. I'd like to go back a little farther than that. I guess that's as far as I'm going to get to go. Let's go back to page 63. Okay. So we described last time that because of this, E is equal to sigma over epsilon, or we could say that E times epsilon is equal to sigma. And if we write it, it's more appropriate to write the standalone variable on this side, on the left-hand side of the equation. I'm just going to start that over this. Okay, this is referred to as Hooke's law. This is a fundamental principle referring only to this behavior in the elastic region. Well, if we take a look at this, we know that sigma, if it's caused by a load, is a P over A. And we further know from our discussion of epsilon that if we had an original length L and then we pull on it and we get an increase in length of del, that epsilon is equal to del over L. So we could write that here, del over L. And so then if we take a look at this, we can see that the equation, this is where we get to page 68. We can write it and solve it for del, and we would get PL over AE is equal to del. Or to write it in the proper form, del is equal to PL over AE. Okay, so what does that tell us? That tells us that the amount that the structural member, the amount in terms of dimensions of length, inches, centimeters, whatever, that the structural member will either elongate or contract is equal to the load applied times the original length times the cross-sectional, or excuse me, divided by the cross-sectional area and divided again by the modulus of elasticity. And that will give you in dimensions of length. Okay? So this is an extremely useful equation in terms of determining the strain, or in this case, the change in length, based on an applied load in axial loading within the elastic region. Okay? Now you can also use this equation and these ideas to determine other things, like you could use it to determine what the load is, what the average normal stress is, and so forth. But basically, the only thing that is not directly measurable would be the value of E. And E, which once again is the modulus of elasticity, or Young's modulus, is a tabulated value. Is tabulated for many, many materials. And so that means that I will either have you look up these values or I will give them to you. They tend to be very large numbers, generally speaking, of the order of 10 to the 6th if you're in PSI, or maybe 10 to the even 9th or 12th in SI. But basically, if we take a look at our textbook, and there's some abbreviated tables here, but in the appendices of your textbooks, there are property tables for different types of material. Okay. And so this is Appendix B, and it's on, I don't know, some page. It doesn't even give a page number. These are all just, yeah, so we just have to go back to Appendix B. But basically, the table is called Typical Properties of Selected Materials Used in Engineering. Now, if you look at it, the tables that have sort of this peach-colored shading are in SI units, and then the tables that are sort of a taupe shading are U.S. customary units. So you can convert easily between these, but you don't have to because they're tabulated both ways. But let's just take a look at what kind of information we have. Okay, steel, for example, if we look at structural steel, ASTM 8386, we have a density, which sometimes comes in handy. We haven't used it yet in this equation. We have an ultimate strength. Okay, that value is here on our graph, right? This is sigma ultimate. Okay, so you look at the units. MPa, that's 10 to the 6 pascals. Compression, it tells you that there's something odd going on there, so the only value we have tabulated is tension, probably because it only responds well in tension. For example, cast iron, then, we have a tension, compression, and a shear. So if the data is not here, it's not an omission. There's probably something about the material that doesn't respond well in that kind of a load. So if you look at steel, for example, you'll see that my tensile yield strength is 250. Okay, so what that tells me, first of all, if I look at those two numbers, I can see that this is a ductile material. And as it turns out, I'm going to yield here at 250, and then there's going to be some kind of whoop-de-doo before it breaks, and it's going to break at a much higher sigma ultimate. Okay, so in other words, I'm going to yield, then there's a period of ductility before it actually ruptures at this point. Here's the modulus of elasticity, which is E. That's the value of E. That is 200 gigapascals, or 200 times 10 to the 9th pascals. We'll talk about modulus of rigidity later, as well as coefficient of thermal expansion and the percent elongation in 50 millimeters. Okay, well, this corresponds pretty closely to epsilon, but it's not a value that we often use. We usually are either solving for epsilon or solving for something else. But the point is, when you need to have the modulus of elasticity E, if it's not given in the problem, you'll check in the tables, and that's what the value will be. And it is kind of freaky that they're huge numbers, 10 to the 6th, 10 to the 9th, you know. But the reason is because if you look at the equation and you look at this, if you pull on a material, the amount of elongation in most materials is going to be quite small, isn't it? I mean, you pull on this, for example, it's not going to increase a foot in length. It's just going to increase this small little amount. So the modulus of elasticity in the denominator of this equation being large corresponds to a small amount in the change in length. Okay? All right, do you guys have any questions at this point? Let's use the equation and do a couple problems. All right. So here in Chapter 2, this is sort of the end of the first set of problems. And we are going to build on this. So if this seems, I wouldn't say easy, but if this seems basic, still want to get really conversant with the ideas because it will become a little bit more involved, where we'll use these in slightly more complicated situations. Let's look at problem 2.2 in your textbook. It says we have a 4.8 foot long piece of steel wire of 1/4 inch diameter, and it's subjected to 750 pounds of tensile load. Knowing that the modulus of elasticity is 29 times 10 to the 6 psi, and that's a very common, 29 times 10 to the 6 pounds per square inch, all manner of steel, many, many types of steel are right in that ballpark in terms of their modulus. So that's pretty common. Determine the elongation of the wire and the corresponding normal stress. Okay, so we have a wire that has a diameter of 1/4 inch. Okay. We are told that the length of this wire is 4.8 feet. And we subject it to a 750-pound tensile load. We know that E, modulus of elasticity, 29 times 10 to the 6th psi, and we ask two questions. What is the elongation? The elongation is del. And we also want to know the corresponding normal stress, in other words, sigma. All right, well, sigma is old hat, right? Sigma is P over A. Our load is 750 pounds. Our A, the diameter is 1/4 inch, so that's pi d squared over 4. So we can put the 4 on the top because it's in the denominator of the denominator. Then divide by pi times 0.25 squared. And my units are pounds per square inch, which is psi. Okay, so on my calculator, oops, let me put this up here. Okay, so I just have 750 times 4 divided by pi and divided again by 0.25 squared. There you are. And so my answer is 1527.888 or 15279 psi, which I could also write as 15.3 psi. This is a better use of significant figures. I'm told that my load is 750 pounds, so I really only have 2 significant figures. So this is 3. This is excessive. Reporting it this way is making stuff up. So we could say 15.3. That just carries an extra 1. The best answer would be 15 psi. Okay, but for computational purposes, I'll carry this out and I'll truncate when I get done with the second part. All right. So I'm given the equation del is equal to PL over AE, but I already have A over E, which is sigma, so there's no point in reinventing the wheel on that, is there? Okay, so I know sigma. I'm going to put that in as the larger, the more significant figure number, pounds per inch squared. Now my length is reported as 4.8 feet, okay? Since this is in inches, and I'm certain this is going to be in inches, I would really like to convert this into inches, because otherwise I'm going to have a unit conversion at the end. So if I have 4.8 feet multiplied by, there's 1 foot per 12 inches, feet cancel out, so I just take 4.8, multiply it by 12, and I get 57.6 inches. Okay. So PL, 57.6 inches. Oh, this isn't P, I'm sorry, that's sigma, over E, which I'm told is 29 times 10 to the 6 pounds per inch squared. Okay, so now before I run the numbers, I'm going to make sure I've got units that I can work with. Pounds cancel out, inches squared cancels out, and I'm left with inches, which is a good number for elongation, isn't it? All right, so I'm going to do 15,279, oops, times 57.6 divided by 29 times 10 to the 6th is going to be 30,347 times 10 to the negative 6. So if I move my decimal place over, I have 1, 2, 3, 4, 5.03 inches. Yep. So this is my value. That's only the one significant figure. I really started out with 2 significant figures. Oh, well, that is significant. No, that is not significant. Okay, so I really wanted, so it's really 0.030 inches. Okay. Now, the other thing I'd like to point out is I'm not really a stickler for the exact number of significant figures. I sort of like to have, I would sort of like to see 1 extra digit. But if you put this answer as 0.0, this is what my calculator tells me, right? This number divided by 1,000,000. 0.030347255. I would mark that like a little zany, so please don't do that. You know, get in the ballpark of the number of significant figures. Okay? So there are my 2 answers. What is del? 0.03 inches. What is sigma? 15 KSI. All right. Do you guys have any questions about that? What's that? Okay, it is really straightforward. I'm glad to hear that. I always hesitate to use the word easy because it's not easy. Nothing's easy. I mean, you can get mixed up a bunch of different ways, but I think this is pretty straightforward. So, a good number. I'll work one other problem, and then I'll post some homework tonight for you guys to do. Let's look at problem 215. This is slightly more complicated, but the process is exactly the same. So on 215, we have a steel rod that is actually 2 steel rods that are welded together. So here's my wall, and I have the portion of the rod called AB, which has a larger diameter than the portion of the rod called BC. Okay. AB is 4 feet long. BC is 3 feet long. The diameter here is 1.25 inches. And the diameter here is unknown. So there's a fun one. Okay, so the diameter here is what I'm looking for. All right. It asks me, it says a single axial load of P is equal to 15 kips. So 15 times 10 to the 3rd pounds. Okay, is applied at the end of at NC of this rod, knowing that E is equal to 30 times 10 to the 6 psi. Determine the diameter D of portion BC for which the deflection at point C, deflection, equals 0.05 inches. All right. So we need to go back to our math and think about what's going on. So what's the total deflection going to be here? Well, it's going to be the amount that this deflects plus the amount this deflects, isn't it? Okay. So the deflection total is equal to the elongation of AB plus the elongation of BC. And we know that the total elongation is 0.05 inches, and that's going to be equal to del, which is P, this is an AB, times L, which is 4 feet, 48 inches, over the cross-sectional area, pi d squared over 4 PL over AE. 30 times 10 to the 6th psi. Plus P L, 3 feet, which is 36 inches, over A, which is unknown. It's called pi times little d of, what is it, BC, over 4, times E, still 30 times 10 to the 6 psi. Okay, now the reason that I wrote it out this way is because a lot of these factors are in common, aren't they, between the two terms? So I can pull them out and not have to do the math. In other words, I could compute this whole big thing, and then I could compute this whole big thing, but really I can pull a bunch of these things out and then put them over on the other side of the equation. So, just using a little algebra, what do we have in common? 15 times 10 to the 3rd pounds. So this and this will come out. This 4 will come out and flip up to the top because it's in the denominator of the denominator. 30 times 10 to the 6 psi also comes out because it's in common between those two, and also pi. Okay, so what do we have left? For our first term, we have 48 inches over 1.25 inches squared. And for our second term, we have 36 inches over my unknown d of BC squared. All right, so what I really want to solve for is the diameter of BC, and it's in a really unfortunate location, isn't it? It's not impossible, but it's like there's a little bit of algebra. The first thing I would do is take this and move it over to the left-hand side of the equation. And when I do that, because it's multiplied through, I invert and multiply. So this is 30 times 10 to the 6 psi times pi over 15 times 10 to the 3rd pounds times 4. So there's my new left-hand side of the equation. My new right-hand side of the equation is 48 inches over 1.25 inches quantity squared plus 36 inches over the diameter of BC squared. The next thing I'm going to do is to find a numeric value here and work out my units. So, turn on my calculator because it turns itself off all the time. Okay, 0.05 times 30 times 10 to the 6th divided by 15 times 10 to the 3rd and divide again by 4. Okay, so my mantissa is 0.025 and I have 10 to the 6th over 10 to the 3rd, so that's 10 to the 3rd. So I move my decimal place. Oh, I have to multiply by 0.05. Sorry, I think I forgot that. I gotta make sure, gotta check my number now. So if I multiply that by 10 to the 3rd, I get 1.25. But I want to recheck this because I'm not sure I did it correctly. 0.05 times 30 times pi divided by 15 and divide again by 4. Yeah, bad answer. 0.0785 times 10 to the 3rd, 1, 2, 3, 78.5, and what are my units going to be? Well, pounds per square inch is pound per square inch. So my pounds cancel out, and then I have inches on the top, inches on the bottom, inches squared on the bottom, so this is actually inches to the -1, isn't it? Which makes sense because we're going to come out with something over here. Okay, so 78.5 inches to the -1 equals, now we're going to take this term, 48 and divide it by 1.25 squared, and that value is 30.72 inches over inches squared is inches to the -1. And then here I have 36 over the diameter of BC squared. Just looking, yep, all right. Alrighty, so these two terms have the same units, so I can just bring this over to the other side of the equation. 78.5 minus 30.72 inches to the -1. So that value is 47.78 inches to the minus 1 equals 36 inches over the diameter of BC quantity squared. Okay, now this is much more solvable, right? I can multiply both sides through by dBc squared and divide through by this, and I get dBc squared equals 36 inches divided by 47.78 inches to the negative 1. Okay, inches to negative 1 in the denominator becomes inches in the numerator. So the value on this side of the unit value on this side of the equation is inches squared. The numeric value is 36 divided by this, which is 0.7534. So all I have to do at that point is take the square root of both sides, and I get that the diameter of BC is equal to the square root of that value.
Would I just cancel off?
Nope. Hang on just a second and I'll show you why. That value is 0.87 inches. So the diameter over here is 0.87 inches. You mean the units? Is that what you're talking about canceling out?
No.
What?
Well, it was square.
Yeah, so I took the square root of this side, and I took the square root of that side.
Square root of the units.
Good? All right, good deal. All right, so do you have any questions about that? So we can use the same idea with two segments of a rod, and we can find the diameter that we're required to keep the elongation at a particular level. Okay. All right. Well, that's it for today, ladies and gentlemen. I'll begin writing the homework number 3 for chapter 2. I'll have a couple of problems from this section so that you can get started working on this. Then don't forget that the homework for chapter 1, which is homework number 2, is due tonight.
We actually had a couple questions.
Sure. Okay. And then we'll continue from there. Okay. And I have a couple of minutes. Maybe I can answer them quickly. If not, I'll be in my office all afternoon. Okay. What questions do you have? Okay. What number is that? 1.6. All right. Yeah. Let's take a look. All right. Yeah, this is a good problem. So what's basically happening here is you have a density, and density is equal to mass per volume. Okay? So if you find the volume of the rod, which is the length times the cross-sectional area, or if it's a cylindrical rod, it's pi r squared times the length is the volume. Okay? Then basically, if you take the density and multiply it by the volume, that's equal to the mass. Now, 1.6 is in metric units. So to find the weight, you have to take the mass and multiply it by 9.81 to get the weight in newtons. Okay? And then when you have the weight in newtons, if it's homogeneous, it's going to act from the center of each of those. Okay? So what you're basically doing is finding a force. So in other words, this is being pulled down under its weight, and this is being pulled down under its weight. And those are the forces. Does that answer your question?
So, once we find sigma, then we can find the length.
Well, the length is going to show up in this equation right here, okay, and again here, and again here. So in other words, you're going to have to go through the whole process before you can explicitly solve for length. But it'll keep showing up as the variable L until the very end.
Okay, so we just keep. Okay.
Yeah. Does that make sense? Okay, and like I said, I will be in my office this afternoon, so if you get working on it and it's not coming together for you, come see me. Okay? All right, very good. All right, ladies and gentlemen, I will shut down, and we will look forward to seeing you either this afternoon or Friday for more fun with Chapter 2.